In this video, we'll look at the solution to section 7 of the 2018 exam, the optimization problem. So the scenario is that we have a rectangle drawn in the first quadrant of the XY plane, and we have a little diagram space here for that. And the base is going to be along the x-axis, so the base will be somewhere like that. The left side is along the y-axis, so we'll have something like that. And then the upper right corner is going to be somewhere based on the graph of y equals 1 over x plus 3 all squared. All right, so the basic scenario is going to involve the graph of y over 1x plus 3 squared. And just remember that is similar to the graph of 1 over x squared, but shifted left by 3. So that would give us an axis over here somewhere. It's going to come down, so it's not super critical that we get a sketch that's too accurate. The main idea is that we are able to think about how we would represent, say, one sample rectangle like that, or another rectangle, maybe out to 3, say. We're going to get different dimensions for those rectangles. Our goal is to find the dimensions of such a rectangle that has the largest possible area. So, given that, let's get rid of our axis here. The key thing I find helpful for optimization problems is look for the phrase where it says the greatest or the smallest, but then focus on the word beside it, the thing that you're asking for the largest of. So here it's area. That is going to be your starting point. We're going to look at areas, and so we need a formula for the area of here, this specific rectangle, this green rectangle. Well, what do we control in that rectangle? We control the x-coordinate, which is how wide that particular region is going to be. And then we control the height, and the height is defined by, well, the y-coordinate on the graph here. So we can start with x times y as our area for this rectangle. All right, once we have that, then we think, well, can I differentiate this and set it equal to 0? Not yet, because we still have two variables, x and y, in this function. We need to be able to reduce this down to one single variable. But then we take a careful look at how we define the y-coordinate here, which is the height of the rectangle. It comes from our expression for the boundary here, x plus 3 squared. That boundary y-coordinate is given by a formula. So we can have the x-coordinate, whatever x-coordinate we pick, the y-coordinate that comes with that is going to be 1 over x plus 3 all squared. Now we're ready for differentiation, because now we only have x's in all the slots, there's no other variables, so we're ready to find the derivative. So let's call this a. So the way that the area changes as we move our x values is going to be the derivative of this. You can do it as a quotient rule or product rule. Let's do it as a quotient rule. So numerator times derivative of the numerator times the denominator minus the numerator itself times the derivative of the denominator all over the denominator squared. And we are going to set that equal to 0 to look for critical points. The nice thing about setting things equal to 0 is that the x plus 3 squared, we can multiply across by it, and it goes away. And so we end up simply with x plus 3. I don't know why I keep saying x plus 2. X plus 3 all squared minus 2x times x plus 3 is equal to 0. We can't really solve that as is, so we better expand it out. We'll have x squared plus 6x plus 9 minus 2x squared minus 6 equals 0. That'll end up with negative x squared in total plus 6x. Oh, sorry, this is 6x here as well. Oh, those cancel. That's nice. And then we end up with plus 9. And so we get x equals 3 or minus 3. Minus 3 is outside the domain, so we can leave it out of consideration. And so it looks like x equals 3 is going to be the value we're looking for. Now, We're asked to do that, and then we're asked to provide evidence that the dimensions we found correspond to a local maximum of the area. Sorry, we also should find the height. So we want a width of 3 and a height which is equal to 1 over 3 plus 3 squared, which is 1 over 36. So it'll be fairly wide and quite shallow, but that is what we think is going to give us the largest area. For the evidence that we have the local maximum, notice it's local, so we can either do the first or the second derivative test. For this particular case, if we take a look at the derivative we found earlier, it's actually pretty messy, right? Imagine taking the second derivative of that with more quotient rule. It just seems like it's going to be ugly. So in this case, I think it's easier to take a look at the first derivative test. So if we have our derivative again, and just notice how we rewrote the numerator. This is the numerator here, and it boiled down to minus x squared plus 9 all over x plus 3 all squared. If we take a look at a little sign chart for that, 0, these are our x values. We know 3 is a transition point. Then when we take a look at the sign of that derivative, dA dx, we know the value is 0 at x equals 3. And when x is really big, like 5, 6, 7, 8, 9, we square it, we subtract, we're going to get a negative number. Whereas when x is small, like 0, we're going to get a positive number. So the graph of a against x is going to be increasing until it hits 3 and then decreasing. So by the first derivative test, x equals 3 is a local max for the area. And that's it.